Okay, so we're going to cover section 10.4. We're going to introduce trigonomic identities. The first identities that we're going to go over are what are known as even odd identities. Okay, all right. So, and we're going to look at the relationship between the cosine of theta and cosine of negative theta, and then the other 6 trig functions as well. All right, so for instance, here. Okay. All right, so for instance, when we have something like this, okay, okay, and if we have an angle theta and an angle, so we'll call this theta in standard position and negative theta, all right, where we go in the clockwise direction. Now, one thing to keep in mind is here I do think of, I always reference theta in terms of an angle between 0 and 2 pi. But this works for any angle that is just coterminal with theta, right? Greater than 2 pi. Excuse me. For simplicity, we just reduce it to an angle between 0 and 2 pi. But all these identities that we're going to go over today, right, also work for angles that are greater than 2 pi. They just happen to be coterminal with theta. Right, now one thing to, the nice thing about the circle equation, right, and the unit circle, is that it has some nice symmetry. Right, if we think here of xy, right, the symmetry here means that the x value is the same, but the y value is negative 1. So when we think of, okay, so cosine of theta is going to be equal to cosine of negative theta. Right, and in the same vein here, we're going to have cosine sine of negative theta. All right, so that would be here. It's going to be negative y, so it's going to be negative sine of theta. All right. Now, a type of relationship like this, where cosine of the negative argument of the cosine has no effect on it, all right, but here it has the opposite of the sine of theta. This is what's referred to as an even function, and this is what's referred to as an odd function, this type of relationship. All right, has to do with their kind of symmetry. When we get more into graphs, we'll see what that means graphically, right? Now, this doesn't just hold for quadrant 1, and you could see we could flip it around. If this was theta and negative theta went that way, then it had the same relationship. But it also worked for an angle out here. All right, or let's say we had an angle here, and this was theta, and then somewhere down here, this would be negative theta. All right, and keep in mind, in both of these cases, they would have the same reference angle, right, alpha. All right, and as we can see here, the relationship between the cosine of theta, the relationship is the same, right? In this case, the x value would be the same, so cosine of theta would be equal to cosine of negative theta. All right, now in terms of the sine of negative theta, whatever this would be, it would be the opposite, right? So in this case, if it's negative, up here would be positive, so we get negative sine of theta. Okay, so that's, again, here we see even / odd identities. And what we're going to see is that, right, cosine and the secant will be the even identities, but everything else is going to have an odd identity, an odd type of function. All right, and again, odd in the sense of it has this behavior here, where we put a negative for the argument, and we just get negative the function itself. All right. Okay, so let's kind of summarize here, even odd. So we saw cosine of negative theta equals to cosine theta. Sine of negative theta is equal to negative sine theta. Tangent of negative theta. Now again here, using definitions of the sine, excuse me, the tangent. All right, and again using the above two properties, this becomes negative sine theta, cosine theta, or tangent theta. Right there we have, excuse me, negative tangent theta. So we have a bit of a proof for tangent of negative theta. And again, simply using reciprocal properties that I covered before, and then the above even odd for cosine and sine. And in the same fashion, we can show cotangent of negative theta would be equal to negative cotangent theta. And again, using reciprocal properties, we can show the following two. Okay, so these will be our even and odd identities. Right? So kind of our building blocks for our identities that we're going to be kind of going through some proofs of them as we move forward here. All right. So the first set of identities here is we're going to go over sum and difference formulas. So we're going to look at sum / difference formulas. And again, here we're gonna work through the proofs here. We're gonna be smart about our proofs. They're gonna involve some geometry and some algebra for the first one, but then we're gonna use what we've already proved to make the next proofs easier and make it work for us, so that we don't have to do as much work ourselves. All right. So a couple things we're gonna need here is, first of all, the distance formula from algebra. So the distance formula, if let's say you wanted to have, there's one point here and another point somewhere out here. All right, we'd like to find the distance between them, d. All right, and that's where the distance formula comes into play. Distance formula derives from the Pythagorean formula, but again, we don't need to go through the whole process of that for this course. But the distance formula is the difference in the x-coordinates squared plus the difference in the y-coordinates squared. And you take the square root of the sum of the difference of the squares. All right, now one thing to keep in mind here is that the designation of x0, y0, x1, y1, it doesn't matter as long as you keep consistent. If this is x0, that has to be y0. You can't mix and match those. All right, but in terms of which one comes first or second, that really does not, it's not important, right? The square and then the root make sure that we always get positives for a distance. Okay, all right, now another common mistake, or a common mistake that I see all the time here, is when students see this, is they automatically go, oh, this is easy, right? That's that. Okay, please do not do that, right? Trigonometric functions do not work like this. As we see, they're circular functions. They have some different behavior that is different from the algebra that we're used to. Okay, so this is incorrect. Okay, so what would be the correct way to approach something that is a difference of angles? Okay, so now to do that, let's look at some geometry here. All right. All right. Okay. All right, and again, I'm going to choose angles that are between 0 and pi, but 0 and 2 pi. But again, these formulas would work for any angles that are coterminal with those angles. All right, so they can be any angle that is from negative infinity to positive infinity, right? We just simplify, so we don't have to keep drawing like rotations around the axis to have it be just an angle between 0 and 2 pi. Okay, so let's say I'm going to draw two rays here. Let me change the color here. Let's start from the origin. I'll call the origin O. All right, and I'm going to call this first angle beta. I'm going to have a bigger angle. And I'm going to call this angle alpha. All right. And we know that if this is our unit circle, which we'll assume that it is here, that this point out here, I'll call it point P, has coordinates cosine alpha, sine alpha. Right? And this one here has coordinates, call it Q, coordinates cosine beta, sine beta. All right. Okay. And so our goal here is trying to find the difference of alpha minus beta. So graphically, that means that in our graph here, what we're looking for is this angle here, right? That angle would be classified as alpha minus beta, right? Okay, that would be the angle here. Okay, so I'm gonna keep that in mind, and also another thing here is I'm gonna keep the distance, now the chord here between P and Q. All right, that's where my distance formula is gonna come into play first in our next, as I reconstruct this angle here. So what I'm gonna do is I'm gonna reconstruct this alpha minus beta in standard position. All right. Okay, so the way I'll do that, excuse me, need a little more space here. Okay, all right. Okay, so we're going to reconstruct this angle alpha minus beta, but I'm going to have it in standard position. Right? So here, what that would look like is alpha minus beta, and I'm going to define 2 points here. The point here I'll call A, which is cosine alpha minus beta, and sine alpha minus beta. All right? And then this point here I'll call B, and again it's the unit circle, so that'll be the point 1, 0. Okay, so it's important to realize here that the way by construction, the way I constructed it now, this angle is the same measure as this angle, right? In terms of radians or degrees, whatever it is that I'm using. All right. Now, one property from geometry is that if the angles are the same, that means that the chord, or the points, the straight line connecting the 2 points on the circle, those also have to be equal. All right. So I'm going to use that property, or that fact from geometry to set up my equation that I'm going to solve for cosine of alpha minus beta. Right? So again, what I said is the angle, again, this is the measure of angle POB, right? POQ. The measure of angle POQ is the same as the measure of angle AOB. Okay, so if the measure of the angles are the same, then the chord or the line segment PQ has to be the same as the line segment AB. All right. Well, I know how to calculate the distance here, right? That's where I use the distance formula. All right. So I'm going to set up here the distance of square root, and the distance of AB, right, is the difference in the x coordinates. So cosine alpha minus beta minus 1 squared plus the difference in the y coordinates, sine of alpha minus beta, and then the y coordinate is not theta, but 0 squared. All right, and this one is AB. I kind of switched it around, but you get the idea. This part is AB here. All right, and PQ, again, the difference in the x coordinates, so cosine alpha minus cosine beta. That is squared plus sine alpha minus sine beta squared. Okay. All right. So now we have an equation to work with, right? One thing I am going to do is we have two roots equal to each other, so let's square both sides here. Kind of make our lives a little easier here. So we have cosine alpha minus beta minus 1 squared plus sine of alpha minus beta squared. I'm going to omit the minus 0 there. And then over here, cosine alpha minus cosine beta squared plus sine alpha minus sine of beta squared. All right, that just eliminates the root by squaring both sides. It just cleans things up a little bit. All right, now the next thing I'm going to do here is I am going to expand these. Right now it's going to look like a big mess, but trust me that it is going to clean up rather nicely. All right, so again, I'm foiling this stuff out here. So here, I'll write one down so you can get an idea of what I'm doing, right? But I'm just not going to write every single one of these out. It's because it just gets cluttered here. Squared, oh, not squared, but cosine alpha minus beta minus 1. All right. So the first term is the same. So we have cosine squared alpha minus beta. Outer term minus cosine alpha beta. Inner term minus cosine alpha minus beta. So that gives me minus 2 cosine of alpha minus beta. All right, and then this one is easy. We just get sine squared. Again, use the alternate form to signify a sine squared. Okay, and here, again, I'm going to expand, but I'm not going to write it out like I did here. Cosine squared. The middle terms will both be cosine alpha, cosine beta negative, so two of them, the two middle terms, are like terms. And then the last term is going to be a plus cosine squared beta. All right, and then I'm going to write it right under here. So again, first term is going to be sine squared alpha. The two middle terms are like terms, so we get minus 2 sine alpha sine beta, and the last term is plus sine squared beta. All right, now this looks like, whoa, there is a lot going on here, right? And there is, but some really nice stuff starts to happen, right? I'm going to use the Pythagorean identity here, right? Where I have, remember, the Pythagorean identity is cosine squared theta plus sine squared theta equals 1. Now, theta is just an angle, so alpha minus beta is our theta. So this allows me to use the, excuse me, I forgot one thing here, right? I did the outer, the inner, I didn't do the last one here. So minus 1 should be plus 1 here. All right, so cosine squared alpha, sine squared alpha, minus beta, both of those together, we get 1. And I have a plus 1 here, and then minus 2 cosine of alpha minus beta. Okay, so that cleans up rather nicely, and notice here, this cleans up really nice as well. Cosine squared alpha, sine squared alpha, both of those give me 1. Cosine squared beta, sine squared beta give me 1. And then we have minus 2 cosine of alpha, cosine beta, minus 2 sine alpha, sine beta. All right. Okay, and another thing we're going to have here is we have 2 plus 2, so we have plus 2 and plus 2 on both sides. We can subtract 2 from both sides, and now we're left with, in other words, the constant terms cancel out. All right, and it cleans up rather nicely, and one more last thing is divide through by negative 2. And we have cosine of alpha minus beta is equal to cosine alpha, cosine beta, plus sine alpha, sine beta. And that is our sum and difference for the cosine. All right, that worked out nicely, right? It looked like a bit of a mess up here, but through, again, using previous identities, we're able to boil it down to this one identity. All right, so we have the difference for the cosine. Now, what about the sum? And again, right, let me kind of reinforce this as we see this is not true. Okay, so whenever you see a difference of cosine, please do not approach it this way. Approach it in this way. Right, use these cosine of alpha, cosine beta, plus sine alpha, sine beta. All right, now what about the sum? Now, we don't have to do all this geometric work, all right. We can just use stuff that we've already have proven essentially previously in this section. All right, so now, what do I do? About cosine of alpha plus beta. Well, instead of redoing this geometrically, one thing we can do is, well, let's work smarter, right? What if I rewrite this as that, right? Now, why would I want to do that? Well, because I know a formula for the difference. Right, the difference we just saw is this. Okay, so let me apply that formula here. All right. Okay, so if we do that, right, cosine of alpha, cosine of beta, in this case, beta takes the form of negative beta, plus sine of alpha, sine of negative beta. All right, so I applied the formula there. All right. Okay, and now I know even odd identities here. I know that the cosine is an even function, so cosine of negative beta is just cosine of beta. And sine of negative beta is negative, so times -1, let's write it out here. It becomes a minus sine of alpha, sine of beta. So there we go. Took us 3 lines once we put in the work in the previous formula to derive this one. All right. And there we go. That is our sum for the cosine, right? This one was nice and easy to get to. All right. All right, now the next thing we're going to look at here is what are called some cofunction identities. The sine and the cosine have a special relationship that we're going to see algebraically, right, using the sum and difference formula, what that means. And in the next section, we'll look at graphically how the sine and the cosine are related. Right, so I'm going to do an example here where I'm going to take the angle in radians pi over 2, and I'm going to subtract theta. All right. And again, I know how to expand on this, right? I've used the sum and difference formula. In this case, it's a difference in cosine, and I know to approach that we have cosine pi over 2, cosine theta, plus sine of pi over 2, sine of theta, where theta is just some angle. All right, I don't really know theta. It represents almost like a variable, just representing an angle here. But I do know cosine of pi over 2 from our unit circle. We saw there from our unit circle, the value of cosine of pi over 2 is 0. We saw here pi over 2, cosine is the x-coordinate, so 0. 0 times anything is 0, or 0 times some real number here. Cosine theta is 0, so this goes to 0. Sine of pi over 2, that is 1, right? The y-coordinate, so 1 times sine of theta, we get sine of theta. So we get this nice property here. Right? And this is what's called a cofunction identities. Now, let's write it down here. So, all right, cofunction identities. I only go through the proof of the cosine, but each one of our 6 circular functions has a cofunction. All right, the first one we've proven, all right, cosine of pi over 2 minus theta is equal to sine of theta. Right, sine of pi over 2 minus theta is equal to cosine theta. And secant of pi over 2 minus theta is equal to the cosecant of theta. And the cosecant of pi over 2 minus theta is equal to the secant of theta. And lastly, tangent and cotangent, they're cofunctions. Goes to cotangent theta, and cotangent of pi over 2 minus theta is equal to tangent of theta. All right. Okay, and now we see how each of these are these cofunctions. In particular, we're going to use this to come up with a sum and difference for the sine. All right, we did it for cosine, and we're going to do this for the sine as well. All right, now again, similar to when we did the sum for the cosine, we are not going to start with the geometric proof. We did that, but now let's work a little smarter, right? We have at our disposal at least this one that I proved, and this that I just stated without proof. But I just need this one, right? I proved that already, and with that, I'm going to figure out the sum and difference for sine. All right, so sine of alpha minus beta. Okay, if I treat alpha minus beta as my theta here, right, because again, just angles, sum and difference, a difference of two angles is just another angle. So using the cofunction identity, I can rewrite this as cosine of pi over 2 minus alpha minus beta. All right, again, I treat that as our angle theta. All right. Okay, and then from here, I know the difference of a cosine, right? But before I do that, I'm going to do a little rearranging here for my benefit here. Cosine of pi over 2 minus alpha. Here, be careful with the distribution here, and it'll be plus beta. All right, so I'm essentially just reassociating my angles here. All right, and we'll see why I want to do this in a second. Okay, once I reassociate it here, I can use my sum formula for the cosine, and the sum formula states cosine of pi over 2 minus alpha, cosine of beta, and sum corresponds with a sum, with a difference in the cosine. All right, so minus sine of pi over 2 minus alpha, and here sine of beta. Okay, and let's bring back those cofunction identities. I can reapply the cofunction identity here. This is the same as cosine alpha, cosine beta, and then that's cosine of alpha. Excuse me, working too fast here. Slow down here. Sine of alpha, right, the cofunction. This is cosine of alpha, sine beta. All right, and now we have a formula for the difference of sine, right? And again, I can't state this is not sine of alpha minus sine of beta. It is this, right? When you see alpha minus beta, this is the only way to expand it. All right, and in a similar way, I won't go through the proof like I did here, but as an exercise, you can try it on your own. Sine of alpha plus beta. Sine beta. Okay. All right, notice that the difference here in the cosine and the sine formulas, well, these are, in the cosine we have the same function. All right, here we have a mix, sine, cosine, and also the minus corresponds with the minus. Well, in the cosine it was flipped. Right here, plus corresponds with the plus. Okay, all right, let's kind of summarize what we have here so far. So in summary here, we have several sum and difference formulas. All right, so we have cosine of alpha. I'm going to use this notation here. Let's kind of explain what this means. So cosine alpha, cosine beta. Okay. All right, so here, this is actually representing two formulas. When we have alpha plus beta, choose the top sign, so cosine alpha, cosine beta minus sine alpha, sine beta. Alpha minus beta, cosine alpha, cosine beta, plus sine alpha, sine beta. Right? And then for the sine of alpha plus beta, this will be sine of alpha, cosine of beta, plus minus cosine alpha, sine beta. Right. Okay, and again, when using the top one, pick the top signal. Right, it's just kind of a compact way that I want to write four formulas, and I can represent four with two formulas here, and just switching out the plus minus. All right, and then the tangent we didn't discuss, so I'll just state here without proof. Again, if you always forget the tangent, you can simply split up tangent as sine over cosine, right, and then work from there. But if you have these handy, you can simply use tangent of alpha plus minus tangent beta over 1 minus plus tangent of alpha, tangent of beta. All right. Okay. And again here, right, if you're dealing with plus, pick the top one, so alternate signs, minus, minus, plus. Okay, so those are our sum difference formulas. Okay, so now we're going to go over these next formulas we're going to introduce, known as the double angle formulas. And again, all these are going to stem from what we've proven before, right? We're going to make our work all right, we're going to, again, use what we already proven to prove even more identities here. The next identity that we're going to prove is the double angle, or in other words, cosine of 2 theta. Right? And again, I want to stress here that this does not work like we would think of an algebraic function where you're like, oh, this must just be cosine of 2 theta. This is not correct. Right? Again, these are circular functions. They have their own rules, and we're here trying to prove what those rules are. Right? So I cannot do that, but how I can approach it is, well, what do I know? Right? I know some formulas for cosine. Well, I can rewrite 2 theta as theta plus theta. Right? That I can do, right? That is something that is within algebra. 2 theta is the same as theta plus theta, but still within that cosine. Right? But I can work with this, right? This I can work with. I have a formula for the difference of angles, or excuse me, the sum of angles, and I'll apply it here. Right? In this case, alpha is equal to beta. So we have cosine theta, plus is opposite signs, right? So minus sine theta. And we have cosine squared theta minus sine squared theta. All right, so that worked out nicely. All right. Okay, and as it turns out here, excuse me, all right, using the Pythagorean identity, sine squared plus cosine squared theta equals 1, there's actually 3 different ways you can write the cosine of 2 theta. And I'll write these here without proof here. So the first way is the one we just discovered. The other way is 2 cosine squared theta minus 1. And the next one is 1 minus 2 sine squared theta. All right, and again, these all come with the substitution of in for sine squared here and in for cosine squared up there using the Pythagorean identity. All right. So that is our double angle for cosine of 2 theta. Right, 3 different representations, and these are equal, right? Depending on what it is that you know about an angle, that's the one that you'll use. Okay? All right, sometimes it's easier to use this one, but other times maybe you don't know sine, so maybe it's easier to use that one. All right, it just depends on the context. All right, now what about for the sine? Okay, and again, same approach here. Sine of 2 theta. I cannot bring that 2 outside the sign, right? That is not how our trig functions work. What I can do is I can apply stuff that I do know. All right, split up 2 theta as theta plus theta. And then use the formula that I proved already, where we have sine of theta cosine theta plus cosine theta sine theta. Right? These are like terms, right? They're the same. So I have one of these plus one of these. Sum them together, we get 2 sine of theta cosine theta. This only has one representation. I can't take advantage of the Pythagorean identity here. Okay, and then lastly, we'll again state here without proof here, the tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta. Okay, and again, if you don't have this handy, you can always split tangent of 2 theta as sine 2 theta over cosine 2 theta, and then simplify from there. All right, so those are double angle identities. All right, and the next type of identities we're going to look over is something called a power reduction identity. Now, in calculus for sure, and in some problems here, this might be helpful. But this is going to be useful when, if you have a sine squared or a cosine squared, and you really don't know how to work with it, or it's just not easy to work with. It'd be nice if it was just a sine or a cosine, right? Not squared. Right, so that's where these power reduction formulas come into play, right? So thinking of our double angle formula, so all we're really going to do here is, let's just solve for cosine squared. All right, so if I solve for cosine squared, I get 2 cosine squared theta equals to 1 plus cosine of 2 theta, and then divide by 2. And we get that. All right, and then similarly, if you use the alternate form of the cosine of 2 theta, we can solve for sine squared theta, and we get, in this case, plus, we get minus over 2. So these are our power reducing formulas. Okay, so again, helpful in certain situations, right? But actually, more importantly, what I can use these power reduction formulas is to develop, let me use this different sheet of paper here, is to develop what are called half angle identities. Right? So these stem from our power reducing, right? Where one thing you notice is this is theta and this is twice theta, right? So thinking of it that way, right? Sometimes we can use to our advantage, let's say cosine squared. Instead of theta, let's call it theta over 2. So using our power reducing formula, it's double whatever that angle is, right? Double theta over 2. Okay, so we see here that this simplifies, reduces the 2. So we have cosine squared of theta over 2 is in fact equal to 1 plus cosine of theta over 2. And taking the square root of both sides, here we do have to be careful. taking the square root of a square, we need the plus minus, and which one we use depends on, again, what context we're given, right? Where does theta over 2 lie, right? Depends on the quadrant, tells us which one we should use, plus or minus. All right, and in a similar fashion, we can use sine of theta over 2. This will be 1 minus cosine theta over 2. And lastly, tangent here we'll get 1 minus cosine theta, 1 plus cosine theta. All right. That concludes our identities for this section.